You type git commit, hit enter, and a new save point appears in an instant. But what actually got created? Not a record of what you changed. Git built a brand new object, gave it a 40-character name, and that name was decided entirely by the contents inside it. To understand why, you have to see Git not as a tool that tracks changes, but as something much simpler and much stranger, a tiny database where everything is named by what it is. Imagine a coat check that refuses to hand you a numbered ticket. Instead, it scans your coat, measures every fiber, and produces a code derived only from the coat itself. Hand it the same coat tomorrow, and you get the exact same code. Hand it a coat with one extra button, and the code is completely different. Git works exactly like this. It takes your data, runs it through a hash function, and the result becomes the data's permanent name. Take a single file. Git doesn't store its name, its folder, or its history alongside it. It compresses the raw bytes of its contents and stores just that in an object called a blob. Then it hashes those bytes to get the blob's name. So a file's identity is its content and nothing else. Two files with identical contents anywhere in your project produce the same hash and are stored only once. But a project isn't one file, it's folders full of them. So Git introduces a second object called a tree. A tree is just a directory listing. Each row pairs a name with a hash, plus a mode telling you if it's a file or a folder. A row pointing to a blob is a file. A row pointing to another tree is a subfolder. Follow those pointers down and a single top-level tree describes your entire project at one moment in time. Now you need to know who took that snapshot and why. That's the third object, the commit. A commit points to exactly one tree, the complete snapshot of your project. It records an author and a committer with timestamps, a message explaining the change, and a pointer to its parent, the commit that came before. That parent link is the thread that turns a pile of snapshots into a history you can walk backward through. But where does the tree for a new commit actually come from? It comes from a middle layer most people overlook. You really have three versions of your project at once. The working directory where you edit files, a committed snapshot that's already saved, and in between them a staging area, also called the index. When you run git add, you're not saving anything permanently, you're copying a file's current state into that staging area, building up the exact contents of the next snapshot piece by piece. Then git commit does something precise. It takes whatever is in the staging area and freezes it into a real tree object, hashing it like any other. That tree becomes the snapshot your new commit points to. This is why a commit captures exactly what you staged, not whatever happens to be in your folder right now. The index is the rough draft of your next tree, and committing is the moment that draft turns into a permanent named object. Here's the idea that surprises most people. You'd expect Git to store the difference between versions, a list of lines added and removed. It doesn't. Every commit references a complete tree, a full snapshot of every file as it existed at that moment. Git stores whole pictures, not the edits between them. The diffs you see when you run git diff aren't stored anywhere. Git computes them on the fly by comparing two snapshots. If every commit is a full snapshot, won't that waste enormous space? It doesn't. And here's the elegant part. Because objects are named by their contents, an unchanged file has the same hash in every commit, so it's stored exactly once and simply pointed to again. Change one file in a deep folder, and only that blob and the trees above it get new hashes. Everything else is shared. You get the simplicity of whole snapshots with the storage cost of just the changes. This isn't a metaphor, you can open it up. Inside your repository, there's a hidden folder, .git/objects, and that's the whole database. Every blob, tree, and commit lives there as a compressed file whose path is its own hash. Run git catfile with a hash, and Git decompresses that object and prints exactly what's inside. No magic, no hidden tables, just content-addressed files on disk. Step back and the shape becomes clear. A commit points to a tree. That tree points to blobs and to other trees. And the commit points to its parent, which points to its own tree, and so on backward. Every arrow is one object naming another by its hash. What you actually have is a graph, where each node is immutable and addressed by its contents. That single idea is the entire foundation of Git. So, if history is a chain of commits, how does Git know which one is the latest? Through something almost embarrassingly simple, a branch. A branch like main is just a tiny text file under .git/refs/heads, and inside it is a single 40-character hash, the name of one commit. That's the whole branch. Not a copy of your code, not a timeline, just one pointer to the tip of a chain. And how does Git know which branch you're on? With one more pointer called head. Head usually doesn't point at a commit directly, it points at a branch. Open a file and you'll often see something like ref:/refs/heads/main. So head points to main points to a commit, and that commit anchors the whole graph. Two small files decide your entire current position. Usually, but head can also skip the branch and point straight at a commit. That's the famous detached head state, and now it's not scary at all. It just means head holds a commit's hash directly instead of a branch name. You're standing on a real snapshot in the graph, but no branch label is following you. Commit while detached and you create real objects, but with nothing pointing at them, they can drift away unreferenced. That's the whole mystery. One pointer aimed one level too deep. Now watch what git commit really does. Git builds a new tree from your staged changes, then creates a new commit object whose parent is the commit your branch currently points at. It hashes that commit to get its name. Finally, it does the one mutable thing in this whole system. It rewrites the branch file to hold the new commit's hash. A new immutable node is added, and the pointer slides forward to it. This is why branching in Git feels instant, while in older tools it meant copying entire folders. To create a branch, Git writes one tiny file containing one hash. That's it! A new branch is 40 characters on disk, pointing at the same commit you're already on. You can make 100 branches in the time it takes to blink, because you're not duplicating anything, you're just adding more cheap movable labels onto the same graph. And this reveals what some of Git's scariest commands really are. Switching branches with checkout doesn't rebuild your repository, it just moves head to point at a different branch label and updates your working files to match that snapshot. Reset slides your current branch pointer to a different commit. Even these feel dangerous, but underneath, the commits never move and the graph isn't rewritten. You're dragging tiny labels from one node to another. The snapshots just sit there, immutable, waiting to be pointed at again. And merging? Remember that a commit can have more than one parent. When two branches have diverged and you merge them, Git creates a new commit that points back to both tips at once, two parents instead of one. That single commit stitches the two histories together while leaving every older commit untouched. The graph doesn't get rewritten, it just gains one new node that happens to reach backward in two directions. Because every commit knows its parents, your history is simply everything reachable by following parent links backward from a tip. Walk back from the merge commit and you can reach both branches and the point where they split. Git never has to store a separate timeline. The structure of the graph is the timeline. Asking what happened is just a question of which nodes you can reach from where you stand now. This naming scheme gives Git a powerful side effect. It's tamper-evident. Suppose someone secretly changes one character in an old commit, maybe the message or a single line of code. The contents are now different, so the hash is different, so it's a different object with a different name. But the commit after it still points to the old hash, and that pointer no longer resolves. The break is immediately visible. You cannot quietly rewrite the past. It goes deeper because a commit's hash is computed from its contents, and its contents include the hash of its parent. So each commit's name depends on the name of the one before it, all the way back to the first. Change anything anywhere in history, and every hash downstream of it changes too. The entire chain is welded together by its own fingerprints. This is the same idea that later made blockchains famous, and Git was doing it years earlier. One detail worth knowing. For most of Git's life, these names were SHA-1 hashes, the 40 hexadecimal characters you've been seeing. Because researchers eventually showed SHA-1 could be deliberately collided, Git now also supports SHA-256, which produces a longer, stronger 64-character name. The hash function changed, but the model did not. It's still the same beautiful idea, name every object by the fingerprint of its contents. Now you can see why Git is fast and why it barely grows. Checking out an old version isn't reconstructing edits step by step, it's reading one snapshot that's already complete. Comparing two commits is comparing two trees, and if a subtree's hash matches, Git knows instantly that an entire folder is identical and skips it. Content addressing turns expensive questions into simple hash comparisons. And when many similar objects pile up, Git does get clever about disk space. It bundles them into pack files and stores some objects as deltas against others, the differences, to save room. But notice this happens underneath, purely as compression. The model you reason about never changes. As far as you and your commands are concerned, every commit is still a full, independent snapshot named by its contents. So here's what Git really is, underneath every command. It's a content-addressed object store, where each blob, tree, and commit is named by the hash of its own contents. Every commit is a complete snapshot, not a diff. A branch is just a movable pointer in a tiny file, and head points at the branch you're on. Stack those ideas up, and Git is one thing, a graph of immutable snapshots welded together by their fingerprints. The next time you commit, branch, or merge, you'll know exactly what's happening behind the curtain. Git isn't tracking your changes. It's storing snapshots and naming them by what they contain, then connecting those names into a graph. Once that clicks, the commands stop being magic spells and start being obvious moves on a structure you can picture. You're not memorizing Git anymore. Now you're just reading it.